Spacecraft are some of the most technologically impressive vehicles ever created, traveling farther and faster than any other man-made object. The Voyager 1 space probe has traveled about 15 billion miles away from the Earth, and the Parker Solar Probe achieved speeds of 430,000 miles per hour as it passed through the upper layers of the Sun. In this video, I'm going to talk about how spacecraft like these travel through space. Some of the topics covered in this video will require an understanding of some basic concepts from geometry, calculus, and physics, but I will provide brief explanations for these. To understand how spacecraft are able to travel through space, we must first understand the basics of orbital mechanics, which governs the movement of any object in orbit around a celestial body. The first person to correctly describe the movement of objects in space, specifically planets, was the 17th century astronomer Johannes Kepler. Kepler made the realization that the path the planets followed around the Sun were not circles, but instead ellipses. He then formulated 3 laws to describe the movement of the planets. Kepler's first law is that the planet's path around the Sun is an ellipse, with one of the foci at the center of the Sun. Kepler's second law is that the planets sweep equal areas of their orbit over equal amounts of time. This basically means that the speed of the planet changes depending on where the planet is in its orbit. At the highest point in its orbit, or its apoapsis, it will be traveling the slowest, and at the lowest point, or the periapsis, it will be traveling the fastest. Kepler's third law is that a planet's orbital period is directly proportional to the cube of its semi-major axis. While this may sound complicated, it just means that the closer planets to the Sun will complete orbits in much less time than planets farther from the Sun. As an example, Earth only takes about 365 days to complete one orbit around the Sun, while Saturn takes over 10,000. Kepler made these laws specifically to describe the motion of the planets around the Sun, but as it turns out, for the most part, they apply to any object orbiting a celestial body. Although Kepler had formulated his 3 laws of planetary motion, he still didn't know exactly what forces were acting on the planets to cause them to move that way. However, a mathematician and physicist by the name of Isaac Newton was inspired by Kepler's laws, and using the acceleration due to gravity at Earth's surface, the distance from the Earth to the Moon, and the orbital period of the Moon, he came up with the law of universal gravitation. F equals g m1 m2 over r squared. This means that the force exerted on one object by another object is equal to the mass of the first object, m1, multiplied by the mass of the second object, m2, multiplied by the gravitational constant g, divided by the distance between them, r, squared. The distance between them is measured from their centers of mass, which is especially important for large objects like Earth. This law applies to any 2 objects with mass, whether it be a baseball on the Earth or a baseball on another baseball. However, the baseballs have such a small mass that there's little varied gravitational force between them, and a slight bump would be enough to knock them apart. But because the Earth is so massive, it can exert a significant gravitational force, even on faraway objects such as those in space. Newton realized that gravity was the only force acting on objects in orbit. Before we move on, I want to bring up that earlier on I said Kepler's laws could be applied to any object in orbit, for the most part. However, there are some cases where the orbit isn't an ellipse. All orbits are in the shape of one of the 4 conic sections: a circle, an ellipse, a parabola, or a hyperbola. This next example will focus on elliptical and circular orbits. Newton came up with a thought experiment to demonstrate how the force of gravity causes objects to orbit. If a cannonball is shot out of a cannon from the top of a mountain, it will travel for a ways before gravity pulls it back to Earth. However, if it is shot out of the cannon very quickly, it will travel so far that the curved surface of the Earth will start to drop away before gravity can pull the ball all the way back down to the surface. And if shot quick enough, the Earth's gravity will be pulling the ball down just as fast as the Earth is curving, and the ball will return all the way back to its starting position, completing a full orbit. Of course, in real life, air resistance would slow the ball down and cause it to fall back to Earth. But if it were done in space where there is no air, the ball would just continue to orbit in a circle. Newton's first law says that an object in uniform motion will continue to move in a straight line until a force is enacted upon it. This means that any object moving in a circle at a constant speed must have some force acting on it. This force is known as the centripetal force, and its formula is F equals mv squared over r, which means the centripetal force is equal to the mass of the object multiplied by its velocity squared divided by the radius of the circle it's traveling in. Centripetal force always points towards the center of the circle. For an object in a circular orbit, gravity acts as the centripetal force, so the equation for gravitational force and the equation for centripetal force can be set equal to each other. Both sides have the mass of the object in orbit in the numerator and the radius in the denominator, so they can both be cancelled out. Then, taking the square root of both sides leaves the equation v equals square root gm2 over r. This is the formula for finding the velocity of an object in a circular orbit. It tells us that a greater mass for a celestial body requires the orbiting object to be moving faster, and that the farther away an orbiting object is from its celestial body, the slower it needs to be moving. Since faster-moving objects have lower orbits and slower-moving objects have higher orbits, it seems obvious that, to move from a lower orbit to a higher orbit, all we need to do is slow the object down. However, this is where orbital mechanics can be a bit counterintuitive. In fact, to reach the higher, slower orbit, we need to speed up twice. Let's go back to our cannon on a mountain scenario. We know that shooting the cannonball very quickly will result in it completing a perfect circle around the Earth and returning to its original position. But what if we shoot it even faster? When we do this, we see that the Earth is dropping away even faster than gravity is pulling the ball down, resulting in an elliptical orbit where the ball travels to a higher point than it was fired from. Thinking back to Kepler's second law, the highest point of an elliptical orbit is also the slowest. So when the ball reaches the highest point in its orbit, it will be traveling slower than the speed from which it was shot with the cannon. And we can see that we've managed to slow down by speeding up. However, we also see that despite shooting the cannonball faster, it still always returns back to the cannon. If we want to circularize at the higher point, we need something that can accelerate while in space. This next section will require a basic understanding of calculus to follow. A derivative gives a rate of change, or the slope, of a function. For example, the derivative of the function y equals 3x is 3. This means that at any point along the function y equals 3x, the slope of the line is 3. In physics, if we have velocity as a function of time, we can find the acceleration by taking the derivative, since acceleration is the rate of change of velocity. An integral can be used to find the area under a curve. For example, to find the area under the function y equals x squared from 0 to 3, we integrate the function from 0 to 3 and find that the area under the region is 9. In physics, integrating is useful when accounting for something that is constantly changing. A rocket accelerates itself by using Newton's second law, which is the conservation of linear momentum. The rocket expels exhaust backwards, and in turn the rocket is pushed forwards. Newton's second law is often thought of as F equals ma law, but there is a broader definition, F equals dp over t, or the change in momentum over time. Usually mass is constant, and since the change in velocity is acceleration, it can be expressed as F equals ma, but since a rocket's mass is constantly changing as it burns fuel, the broader definition is needed. The formula for conservation of linear momentum of a rocket is the change in fuel mass times the exhaust velocity of the fuel is equal to the mass of the rocket times the change in velocity of the rocket times -1. Dividing both sides of the equation by the mass of the rocket and then integrating both sides gives the equation delta V is equal to the velocity of the fuel times the natural log of the initial mass divided by the final mass. This equation is known as the ideal rocket equation, and it is one of the most important equations in rocket physics. It tells us the delta V of our rocket, or how much we will be able to change the speed of the rocket, which is crucial in knowing how far the spacecraft will be able to go. Once we know the delta V of a rocket, we can send it to space, accelerating up, then sideways until we reach space, and then accelerating sideways again until the rocket has reached a circular orbit. After this point, the spacecraft can be sent wherever we want to send it, just as long as we have enough delta V. This video only covered the very basics of rocket physics and astrodynamics. There are many other interesting topics beyond the scope of this video, such as specific impulse, transfer orbits, and gravity assists. If learning about space travel is something you're interested in, I would highly recommend looking into these things. There are also video games such as Spaceflight Simulator and Kerbal Space Program, which have physics engines that can accurately model orbital mechanics. and provide a much more intuitive understanding of how objects move in space. I would highly recommend learning more about how spacecraft travel through space because it gives the opportunity to understand how humanity is exploring the final frontier.